All right, thank you, gentlemen. So I'll briefly introduce our various panelists, starting in the middle with Dr. Byron Pipes, who was elected to the National Academy of Engineering in 1987 in recognition of his development of an exemplary model for relationships between corporate, academic, and government sectors to foster research and education in the field of composite materials. Dr. Pipes developed the Composites Design and Manufacturing Hub to meet the simulation needs of the composites industry, and in 2013 at Purdue University, which you proudly represent today. And he currently leads the Indiana Center of the Center of Excellence of the Dewey Institute for Advanced Composites Manufacturing Innovation. Thank you for being with us, Byron. Next to you, on the left, we have Bug McCarthy. He's a senior consultant at SRK, which is a world-leading international consulting practice, providing focused advice and solutions to the earth and water resource industries. As a professional mining engineer, Bob has 30 years of experience in mine operations and engineering, asset management, technology design, and implementation. Thanks, Bob, for being with us. And finally, Raja Sengupta, who is the principal feature leader and global technology specialist for aerodynamics at the Volvo Trucks here in North America, responsible for both product development and aerodynamic certification. Raja has 20 years of experience in the field of aerodynamics and CFD and has been with Volvo for the last 12 years. He was involved in the regulation development for greenhouse gas, phase 2 for heavy-duty vehicles, and with the DOE-sponsored Supertruck programs. So welcome, gentlemen, and thanks for making yourself available. So in this short panel, we'll try first to explore in your respective areas how science in the age of experience can provide tangible answers to the challenge of a sustainable planet. The three of you combined, you sort of represent the value chain, right? From resource extraction or raw materials to the transformation of those materials into materials with enhanced property, and finally assembly in the manufactured products or systems which deliver a valuable function to people. So we'd like to understand with you how sustainability has become a pervasive theme in what you do. In other words, specifically, how is science helping you deliver on sustainability objectives? And maybe I'll start with you, Bob. You're in the business of natural resources, and so it obviously plays a critical role in the discussion around a sustainable planet, because we know we have finite resources. So can you tell us, how does mining fit in a sustainable planet vision, and how does mining can leverage science to reach that vision?
Thanks, Will. I'll answer that from two perspectives, mining and sustainability. With growing human populations, the growth of society, there's a requirement that we innovate to reduce our collective footprint. And often with innovation comes development and use of new materials, and those materials need to be sourced from somewhere, and mining is that prevalent source. So we play a key role in the overall sustainability planet objective. But to look more inward, how does mining fulfill sustainability in its own right? And for that, we have to look to science and how do we reduce our footprint. We look at footprint in two ways. One is the physical footprint, and the other is perhaps our energy or our water usage footprint. We're ever looking at processes to reduce those footprints. To be more specific, I'll draw on some examples from the mining value chain. Mining consists largely of the mining process itself, mineral processing, which harvests the actual minerals of value, and then the waste management at the end. So if we look at mining, mining is done both from surface and underground. For surface mining, we go after the valued mineralized material, which we call ore. But to get to that ore in surface mining, we also have to remove a lot of waste rock. And that waste rock has to be disposed of. Typically, that's done with large haul trucks, which haul the material to waste rock facilities. Now that has two problems. It increases the physical footprint, but also the greenhouse gases associated with the haulage is one of the biggest challenges that faces mining, open pit mining. So along those lines, science and engineering are coming to bear to look at things such as in-pit crushing and conveying, which attempts to remove the haul trucks out of the mining process and rely more on electricity and conveyors to move material around. If you look at underground mining, by its nature, you don't have the physical footprint that you have with open pit. And so there is actually a positive there and an upswing of adoption of underground mining, both because actually surface mineable resources are reducing over time, but there's also this benefit of the reduced footprint. So there's a lot of focus on underground mining, science coming to bear to both find these deep underground resources, but also to make the mining process more efficient, safe, etc., by new types of machines in that environment. As we move down the value chain to mineral processing, on mineral processing we have the requirement to crush material to very fine sizes to liberate the valued material. That takes an awful lot of energy, particularly in crushing and grinding, which we call comminution. So there's a lot of focus on how do we do that in a more focused, differentiated way, only crush and grind the material that you ultimately need to extract the final material out of, because a lot of what's in the ore that goes into a mill is actually waste. Along the process of that crushing and grinding, there is at any time a size of a particle or a batch of material that no longer has sufficient mineralization in it to warrant its further processing, its further use of water and energy and so forth. There is a lot of focus on that right now. I'm actually personally very involved with it. It's the area of pre-concentration and ore sorting, where we're trying to remove waste as early out of the process as possible. And then finally, when we grind the material down to its final size and we liberate the valued mineral out of that, we're left with waste that we now have to dispose of. It's very, very fine. Because the final separation processes are water-based, this waste is in a slurry form, so it gets pumped to facilities, otherwise known as tailings dams. A lot of notoriety around that out there. There's been some recent disasters, both in British Columbia and Canada, as well as in Brazil. There is a huge focus now in industry to bring to bear science, engineering, everything to look at how can we do things different? How can we dewater this material and place it in more solid landforms so that we don't have these sort of legacy issues?
Thank you, Bob. So it looks like there's no shortage of opportunities for science to help make this whole value chain much more sustainable than it is right now. Yeah. Thank you. Byron, if I turn to you, in fact, in the Better Living section earlier today, we saw great examples of how material science is really helping a lot. So in your practice, can you help us understand in the process of creating the materials of the future, how does science indeed contribute to greater sustainability?
Thank you very much. I'm delighted to be here today to share a few thoughts with you about how engineers change the world. As we heard each talk today, you kept hearing the word, we will need to solve this engineering problem in order to achieve this objective. How do we do that? The process is very simple. We start with engineering talent, and we build that talent throughout the world, because we cannot accomplish this objective that we've been discussing today, either in production of new polylactic acids or the understanding of the mining industry and the revolution of that industry, without the engineering human talent that's going to build it. I sit very much in a seat, as you might guess, at a university where the engineering talent of the future is everyday present. I see them, I have seen them in this process for over 4 decades. Let me just take you through a little discussion about how engineering was when I was a student. Many of you were engineering students, or you were science students. You know what this world was like. It was very much a hands-on empirical world, a world in which we had the thermodynamic laws, certainly. We had the fine material science laws in front of us, but we didn't really have the power to take those laws and move them into answers quickly. This took years to develop processes related to our current energy usage, all of our refining technology in the petrochemical industry, all of our chemical industry. These were very empirical, though they were fine scientific bases. They took engineers to develop them, to build the facilities to answer the questions. So I think we're very much thinking about the human talent, the ideas, but the speed at which those ideas can be developed. This is especially true in advanced materials today. We know what it takes to develop the modern metals. We know what their acquisitions are involving. But what can we do with lighter material systems? What would they do for us? As a matter of fact, if you looked at each of the discussions of energy use, there was, I believe, a vehicle was the primary responsible for the negative production, or pardon me, the positive production of CO2. If we could simply take the weight of those vehicles down by an order of magnitude, we could change that substantially. So how do we do that? How do engineers do that? And by the way, the most important thing I think that was said earlier in the two talks was, how much time do we have to do this? We've had a century to get where we are in the Industrial Revolution. We don't have a century to get to where we need to be. And therefore, the rate of learning, the rate of application of science to these problems is the real issue today. It isn't about whether we have the ability to learn and grow and develop new ideas. It's how fast can we do that. I'm going to have more to say about that in a moment when I think about and share with you about how Dassault Systèmes simulation can answer that question. How simulation is at the very base of these answers. There is no industry, no development that we've had so far in the world that will have as much impact as simulation will have on the revolution that we need. And that revolution will be led by engineers who are using the best tools they have to get the answers as soon as they can get them, because we have to have them. Material science is at the base of that for sure, but it's not unique. There are many pieces of engineering. The interesting thing to me is that we now can develop materials all the way starting with the atomistics. We can include each scale of development and behavior and understand that through simulations. Really for the first time, these scales are being connected in some very powerful ways, and I'll say more about that in a moment.
Thank you, Byron. In your answer, you actually mentioned vehicles, so it's a natural transition to Raja. And also, Jennifer Wilcox in her talk did mention transportation, as that industrial sector where it's going to be quite tough to reduce the footprint. So, Raja, in your experience in the design of heavy-duty vehicles, trucks, can you provide examples of how you can still actually have a positive handprint thanks to science?
Yes, absolutely. Not just at Volvo Trucks, but at Volvo, care for the environment is one of the core values. So that's not just in tailpipe emissions, but even in manufacturing. The Volvo truck plant in Virginia achieved carbon neutral status November 2014 by using land-based methane from nearby landfills. But my role is focused on engineering, as Byron said, aerodynamics in particular. And so when you look at tailpipe emissions, on US highway trucks, about half of the fuel efficiency is driven by aerodynamics. So that means every % I can reduce the aerodynamic drag, I get 0.5% fuel efficiency benefit. So that adds up really quickly. And for trucks, unlike cars, these are tools that our customers make money from. So every dollar we save them on fuel is a return on their investment. So we at Volvo take it very seriously. So what have we done? In the traditional process, like Byron, you were mentioning, we would have physical models, prototypes. And by the time we would make a scale model of a truck, take it to the wind tunnel, test it, the design guys have already moved forward. So this process wasn't working for us. A full-scale new truck development would take on the order of 5 to 10 years. Clearly, the pace that we are talking about, that is not met by this process. So we started looking at simulation. I've been with Volvo the last 12 years, and that was kind of my push to get simulation-driven development, at least for aerodynamics. So since 2011, we have not done wind tunnel testing. We've relied on Dassault Systèmes product, PowerFlow, to do our aerodynamic development, and we do final verification with a full-scale production model that goes into field economy testing. And over time, with repeated verification and validation, we now feel confident enough to deliver the targets that we have to meet. So science is at the core of what we do in that sense. But let me give you a couple of examples of how that has translated. So other than regular product development, we worked on the DOE-funded super truck projects, where basically they gave us a blank slate to say, okay, how would you get from today's product to a 50% more efficient transportation system? This is only focused on highway trucks, so not mining trucks yet, but we'll get there. We blew that target out of the park. We achieved 88% freight efficiency improvement, that is in ton miles per gallon. And we didn't build a single physical prototype along the way. It was done completely virtually, and we delivered the product and met the target using simulations. Not only that, it also set the stage for what could be achieved in the near term. So when EPA and other agencies were setting up the standards for greenhouse gas phase 2, they looked at Supertruck to say, okay, these are technologies that are readily available. And what's neat about aerodynamics is you're not coming up with new material. You're not coming up with new complex mechanisms. You're taking a shape and making it more efficient. I mean, you could get there using clay modeling and wind tunnel testing, but it would take you 10 times longer. The simulation gives you the visual cue, gives you the feedback that you need to say, this is where I need to focus to change the design. So the technologies we showed with Supertruck basically translated to the regulations that will go into effect in 21. And greenhouse gas phase 2 alone will reduce CO2 from the heavy-duty transportation sector by 1.1 billion metric tons of CO2.
So that's tangible, very tangible.
Very tangible. So, of course, we are not carbon neutral. We cannot be. The long-haul trucks will continue to be fossil fuel powered for the foreseeable future. But there are other targeted segments where we can come up with more efficient solutions. But the beauty of this is what I do on the aerodynamic side applies as much to electric vehicles, in fact more, as it does to diesel. So that 2% to 1% that I said on the fuel economy, aerodynamics to fuel economy, translates to range on a battery electric vehicle. And just to echo on Byron's comments on the lightweighting, every kilogram or pound, some of you are metric, some of you are not, but every little bit of weight that we take from the product, from the tractor itself, translates to payload for the customer.
It's a clear win-win,
Yes.
essentially.
So in everything we do, science and simulation is driving the development.
Okay. Another angle I want to address it was the fact that sustainability is everyone's business. It cannot be just dealt with in isolation from others. So the question I wanted to ask you was whether the imperative of a sustainable planet can help overcome the existing barriers that exist in business or in research between people, because there's competition in both of these spheres. So maybe I'll start with you, Byron. In the type of work that you conduct, you must be exposed to a vast ecosystem. And so how do you see here, do you see sustainability as becoming a compelling reason for people to truly collaborate?
No question in my mind, as we think about the problems that have been addressed today. They're all interdisciplinary problems. There are many fields represented. What unifies them, and what is being unified very much by Dassault, is simulation. If all of the science and engineering can be brought into a common language, if you will, and we have, each of us can speak that language, when we solve important problems, this is going to be a huge accelerator for solving these problems. I think very much simulation is at the platform or at the base of the answers that are coming for us, both in the rate in which they can be developed and the breadth in which they can be covered. Each of us was taught, as we went through school in engineering and science, specific disciplines. Often we learned a few, not too many, very, if you will, siloed learning. But when we found ourselves in the world trying to solve problems, it was an interdisciplinary world. a world that continues to be, and if anything, tomorrow, more interdisciplinary. Therefore, we need tools. We engineers need tools that unify these disciplines in a common platform that will deliver the answers that engineers need with the platform that will be developed.
I think we have a platform for you. I think so. Bob, in the world of mining, which has traditionally been considered to be conservative and siloed, do you see some practices evolving because of this agenda that we've been talking about?
Well, certainly, mining is conservative. We often joke that we're in a race for second. Innovation, while it's out there, is very risky. It's not that mining is risk adverse. I think it's just an overload on risk. We start off needing to identify the nature and quantity of the material in the ground, and we do that from a very few data points. Then we have to predict what the commodity prices will be in the future, and of course that's fraught with risk and uncertainty. So high-end innovation is just another layer of risk, which is sometimes difficult for mining to get their heads around. However, having said that, mining companies are recognizing that they can't go it alone to solve some of the challenges that I outlined earlier in my first question. So you are looking at opportunities for collaboration. Some of it's formalized, such as in Canada, there's the Canadian Mining Innovation Council, and in Australia, there's the cooperative research centers. These initiatives are co-sponsored by government. They tackle very specific problems where mining companies come together and they basically put their competitive nature aside and they collaborate together on that. Within mining companies themselves, there are the silos, the interdisciplinary silos. That's always been there, but I see that breaking down more as we try to work together with common goals and problems to become more sustainable.
Thank you. Raja, I guess given the nature of your work, for you this cross-disciplinary approach is like almost obvious. And what do you see as the greatest enablers to push it further?
Yeah, it's the nature of the beast in product development. I own one feature. I have to fight with 10 other feature leaders that are fighting on ergonomics, visibility, you name it, right? So the problem right now is your product development cycle is only as fast as your slowest feature. So I could get my design frozen in 6 months, but if the other feature has to wait for a physical prototype for 3 years and come back and tell me you need to change this, that derails the whole process. So what we are counting on is basically simulation across the board. Everybody gets on the board with virtual development, virtual verification to a certain extent. There are certain areas that we will not give up on. Crash, safety, this is high priority for Volvo, so we will continue to do physical prototyping there. But in many other areas, we are using VR, AR, to basically capture risks early in the project so we don't have late changes that cause not only project delays, but basically we lose our time to market. So simulation and a common platform are the key for collaboration, and it's a language that we all speak. That's what's nice about it. So I'm hoping that, today we have offices full of monitors. When my kids go to work, there'll be offices full of headsets, VR and AR headsets. So that is almost here. I mean, we're already getting into that phase of transition. When I started working, we were transitioning from physical models to digital models. Next one is going from 2D to 3D immersive experience. So it's an inevitable progression, but it couldn't have come sooner because that's what we need to meet the challenges that are coming up.
Okay. You mentioned your kids.
Yes.
So nice segue to the third and final theme for this talk, which is the workforce of the future. The reason we want to have this theme addressed in our panel is because throughout the world we see the young generation embracing the systemic agenda almost as the battle of their generation, with of course levels of awareness that vary from country to country. But clearly this really suggests that the workforce of the future really wants to see how they will contribute to sustainability in very practical terms. And as a result, the question is for us here, how can we leverage science to fulfill these aspirations and indeed ensure the workforce of the future will understand the meaning of what they do and how creative it is to sustainability objectives. So maybe I'll start with you, Bob. And Bob, I'll be very blunt. I'll ask you, can science make mining great again and seduce the younger generation?
Well, I would argue that mining has always been great.
Of course. Of course, didn't expect a different answer from you.
Certainly it is evolving. Certainly there is public perception that mining is old school, dirty, unsafe, etc. By the way, it's anything but unsafe. It's one of the safest industries you could ever get into. But that said, it's not cool, or at least that's the perception. So how do we get the young, bright minds engaged with mining? Terms like big data, digitalization, biogenetics, AI, all those things, they are actually in the vocabulary of the modern miner. A lot of it, excuse me, a lot of it is developing, but nonetheless, it holds lots of opportunity out there for the young minds. And let me draw a specific example. Mining is going the autonomous route. There's no questions about it. Both underground and surface mining, you're looking at haulage by operatorless vehicles, operatorless drills, and so forth. Well, that creates a whole new skill set required, one that requires a higher education, higher levels of training. And it's a direct appeal to the perhaps the PC gaming, video gaming generation, where a lot of what you're going to do now is over the wire, over computers. And in fact, to take that one level further, with that technology and that science, you're able to now not have to be located at the mine itself. You can be in a command and control center in some other location that perhaps is more amenable to your personal desires. It's not in an inhospitable remote mining location. So there's a bonus for getting younger generation into the mining, and it's obviously through science and innovation.
And you, Raja, isn't mobility and transportation already so much high tech that you face hardly any issues in attracting the workforce of the future, or is it an issue?
I mean, it's a kind of a perfect convergence, if you will, because we know we are a big part of the problem in terms of emissions, tailpipe emissions, but we can be a big part of the solution. And Volvo is committed to that, and we are attracting engineers, young engineers to start their career. As Bob mentioned, when I started, we had gearheads and fans of hot rod. Now we have AI people coming into the truck world. So, it's been quite a transition, and like I said, with the move towards virtual product development, simulation-driven, AR, VR-driven, it's only going to attract more young people into the industry. My kids, when I just showed them CFD simulation results, this was when they were 4 or 5. They just loved it. So they both want to work at Volvo now.
There you go.
But we'll see how that goes.
All right. And finally, Byron, with the vantage point that you have when you're seeing all these students, do you detect in your students today now this notion that sustainability does matter in what they will be doing in the future? And do you think that science can help answer their thirst for sustainable outcomes of what they do at work?
Oh, I think we've all agreed to that point for certain. I think what I see in the student that's coming today is a hunger for tools to solve these important problems, to learn about them, to learn how to use them. And if you think about what's available today compared to what was available when I was a student, it's enormous. At the same time, it's a huge both opportunity and challenge of how we use simulation to teach. This is, I think, the next wave in education. We're going to see it because education will continue the rest of our lives. Simulation is very portable for learning.
All right. Well, gentlemen, I would like to thank you for sharing your insights with us. It came from a